This video is about relationships between two or more sets of data. In statistics, when we say that two sets of data are related, what we mean is that we know an algebraic function whose graph describes or explains the relationship between data in the two collections. For example, this table and graph show two collections of data where there doesn't appear to be any function that fits the pattern of data points in the graph. Or, here is a graph of data points where a straight line describes the relationship between the two collections. Or, there are other data sets where a straight line almost but not quite fits the pattern of data points. So, in these kinds of situations, we'll need to be able to measure the goodness of fit for various functions that come close to fitting the data. The functions don't necessarily need to have straight line graphs. For example, their graphs might form parabolas or other shapes. But, in any case, when a function does a good job of fitting data, we say that the data are strongly correlated. The topic we'll be investigating sometimes is called correlation and regression, and, just as in the case of centers, or points of best fit, there also may be several alternative ways that might be sensible to define what you mean by a line of best fit. For example, here is a graph showing 5 data points, which are labeled A, B, C, D, and E, and your task might be to move the points L1 and L2 so the green line minimizes the sum of the distances to the 5 points. In the first case, the line of best fit might be defined to minimize the sum of the simple straight line distances from the points to the line. In the second case, the line of best fit might be defined to minimize the sum of the squares of the distances from the points to the line. In the third case, the line of best fit might be defined to minimize the difference between sums above and below the line. In other words, this definition finds the sum of the red lines. Then, it finds the sum of the blue lines. And then, it minimizes the difference between these two sums. And, in the fourth case, the line of best fit might be defined to minimize the difference between sums of squares above and below the line. In other words, this definition finds the sum of the yellow squares. Then, it finds the sum of the orange squares. And then, it minimizes the difference between these two sums. What you will discover from these investigations is that, in general, these 4 lines are not the same. Furthermore, different definitions are based on different assumptions. And, these differences might lead to significantly different results. So, it is important to be aware of alternatives and the assumptions that they presuppose. Here is a table and some graphs that report results from several questionnaires, similar to the kind you can find on the internet, or if you go into a barber shop or beauty shop. Some questionnaires ask you to answer some questions. And then, they claim to tell you something like how hot you are, or whether you're friendly, shy, or impulsive, or whether you have some other characteristic. Or, slightly more scientific questionnaires, such as a Myers-Briggs test, might claim to diagnose your personality type. Sometimes, high scores are considered to be good. Sometimes low scores are considered to be good. And sometimes middle scores are considered to be good, such as when it's desirable to have a balanced diet. Sometimes the spread of the scores is large, like 50 to 100. And sometimes, the spread of the scores is small, like 0 to 10. In any case, it's sometimes useful to measure the closeness, or distance, between attributes. For example, you might want to combine the measurements from indicators that seem to be measuring different aspects of the same thing. Or, you might want to eliminate indicators that seem to be measuring the same things. This animation shows a situation where 6 scores of some type are given. If all you know is the value of the 6 scores, and if you were asked to guess the value of a new score, your best guess might be the average of the scores that are shown. But, if you were given more information, then you might try to find a line of best fit, which could be used to make predictions. For example, if this line seems to provide a best fit with the data, then the points on the line show what score you would have predicted for each value on the horizontal axis. Here are several different ways that you could measure how well this line fits the data. First, you could calculate the sum of the red lines shown here. they show the simple straight line distances from the line to each of the data points. So, this sum can be called the unexplained variation because the points on the line show variation that is explained by the rule associated with your line of best fit. Then, if you want to compare this unexplained variation with similar measures with other lines, or other measures or other graphs, then you need to stretch or shrink the unexplained variation by dividing it by the spread of the original data points. So, the unexplained variation divided by the observed variation is a measure of how well your line explains the observed data. Or, you could have measured the sum of these black lines. They tell how much your predictions vary around the center of the observed values. So, this sum can be called the explained variation. This means that another way to measure how well this line fits the data is to divide the predicted variation by the observed variation. This method is equivalent to the first method. Or, a slightly different method involves finding the sum of the squares of all of the preceding differences. So, using sums of squares instead of simple straight line distances, the sum of explained squares divided by the sum of observed squares is called the correlation coefficient. Or, the sum of the unexplained squares divided by the sum of observed squares also could have been used. This is because the sum of the explained squares plus the sum of the explained squares is equal to the sum of observed scores. You can investigate all of these relationships by using this Tinker plot simulation. First, you can run the sampler to see a new set of data. Then, you can move the line so that it provides a best fit with the data. You can tell when you've found this line by asking Tinker plots to record the sum of the differences between your line and the observed data points. This sum is recorded in this table in the column called Unexplained Variation. Now you can measure how well your line fits the data using the variability information that's given in these three graphs. The first graph shows the unexplained variation, that is how far the observed data points are from your line. The second graph shows the observed variation of the original data points around the mean. And the third graph shows the variation of your predicted points around the mean. So, you can measure how well your line fits the data by either 1. Dividing unexplained variation by observed variation, in which case low scores are good, or 2. Dividing explained variation by observed variation, in which case high scores are good.